Action. Okay, hello everyone. Today I'm going to talk about an auditing language framework for preventing cascading failures. This is a joint work with Ruzika Piskach from Yale University. So today's cloud services rely on redundancy to ensure the reliability. For example, a lot of famous cloud providers replicate their service data and status across different racks or data centers. However, cloud outages still occur very frequently in recent years, and the question is, why replications do not help? A lot of investigations demonstrate that most of the large-scale cloud outages were caused by cascading failures resulting from unexpected common dependencies. What is a cascading failure? Let me show you a real example about cascading failure. Happened several years ago in Amazon AWS. In Amazon AWS, EC2 service relies on EBS for storage support. And some application providers, for example Netflix, replicate data across different virtual machines running on physical machines in EC2 layer. In this outage event, bug happens in EBS cluster, and this problem leads to cascading failures across physical machines in EC2 layer, undermining the redundancy efforts made by Netflix. Cloud providers handle cascading failures using different techniques, such as provenance systems and troubleshooting systems. All the existing efforts try to address this problem after the service outage occurs, which means the administrator try to diagnose the root causes when they notice the problem. One problem of existing efforts is time-consuming to recover the failures or diagnose the root cause in a large-scale system. The second problem of existing efforts is they cannot prevent failure downtime because you at least violate the SLA signed with your customers. In human being world, disease prevention is better than diagnosis. So the goal of our big project is to prevent cascading failures before the service outage occurs. So in this talk, I will cover two parts. In the first part, I will describe the first effort towards this goal. I published this paper in OSDA 2014, which is Indus system. And in the second part, I will talk about the auditing framework, which is a language framework and appeared in Uppsala this year. So here is the typical service runtime. At the very beginning, you set up your service. In some time of point, you meet the problems. As what I mentioned before, the post-failure efforts can diagnose the problem. But Indus is a very different system. So the Indus can recommend the most independent redundancy configurations to administrators when they set up the service. So in this case, Indus can significantly avoid the potential cascading failure risks. Let me show you a workflow of Indus system. So in the first step, Indus can automatically collect dependency data of the target environment, including software and network dependencies. After that, Indus can build the fault graph model to represent the target system stack, and then Indus evaluates the independence of all the alternative redundancy configurations. So in this case, administrators can select the most independent one for her service setup. Let me show the process of generate the fault graph in Indus system. First, Indus system generates the root node of fault graph, which is redundancy configuration failure. And then Indus use AND-gate to connect redundant servers in the target environment. So AND-gate means if all the child nodes fail, then the parent node will fail, which is exactly the meaning of redundancy. And then Indus use OR-gate to connect different types of dependency. So OR-gate means if at least one child node fails, then the parent node will fail. Underlying each type of dependency, Indus use different logical gates to connect the corresponding components. For example, Indus use AND-gate to connect redundant network paths. After generating the fault graph, Indus use Monte Carlo algorithm to simulate the potential cascading failure and then quantify the independence of this alternative redundancy configuration. So far, I have presented the workflow of Indus in a very high-level description. So there are several problems in Indus system. First, it's hard to express diverse auditing tasks using Indus system. For example, administrators may want to identify the potential cascading failure risks. Second, the fault graph analysis approach in Indus is time-consuming. So administrators may want to support the auditing in runtime. For example, during the service runtime, administrators may change network path or upgrade your software. So whether the administrators can check each snapshot of interest during their service runtime. Finally, even if you know where is the potential risk, it's still hard to fix the problem without introducing any new problem. We propose our solution named the Rep Audit, which will appear in Uppsala this year, and Rep Audit can address the 3 problems I just mentioned. First, Rep Audit proposes a new domain-specific auditing language. Administrators can use this language to write auditing programs to express different auditing tasks. Second, Rep Audit proposes very fast fault graph analysis approach based on different size solvers. In this case, administrators can quickly check each snapshot of interest. Finally, our framework proposes the automatic repair engine for administrators. In this case, administrators can get the improvement plans if she notices any risk in her current deployment. Let me show you a simple example about how to use our system to identify unexpected common dependencies. For example, in this toy example, we have a bottleneck here, and that can lead to cascading failure. And we want to identify it ahead of time. So in our framework, we have an auditing engine. Because we proposed a new domain-specific language, so administrators can write the program using our language. And then our framework relies on Indus to automatically get the dependency data and generate the fault graph. Our framework has a very quick approach to analyze this fault graph and return the results to administrators. In this case, administrators can deeply understand the current snapshot of interest. So let me show you our contribution. The first contribution is auditing language. So here's the definition of the grammar of our auditing language. The most important part is the primitives. We do a lot of investigations to real-world cloud outage events, and we propose the corresponding primitives. And using the primitives, administrators can write auditing programs. The second contribution is we can quickly analyze the fault graph. So before I describe the details, I need to introduce an important terminology, which is the risk group. In a fault graph, a risk group means a set of leaf nodes whose simultaneous failure will lead to the failure of root node. So risk group is exactly dependency we want to detect. And in this example, A2 is a risk group, and set including A1 and A3 is another risk group. But A1 or A3 itself is not risk group. So we actually reduced identifying unexpected dependency to the problem of finding out risk groups in fault graph. However, this is a hard problem, and there have been 2 categories of efforts in this direction. But in the first category, the approach can offer a very accurate result. Unfortunately, it's very time-consuming in large-scale system. On the contrary, the second category can offer very fast analysis approach, but they cannot provide accurate result in the large-scale system. So our target is to simultaneously achieve efficiency and accuracy in large-scale system. And how we do this? Our key insight is transform the fault graph into Boolean expression, and extracting risk groups can be reduced to the problem of extracting satisfying assignment from Boolean expression, and all the leaf nodes in fault graph can be looked at as the Boolean variables in the Boolean expression. So we can put the Boolean expression in the size solver and get what we want. But unfortunately, this world is not so lucky enough, and standard size solver can only output an arbitrary satisfying assignment, and what we want is to get a top K critical risk group. So how we do this? And we rely on a very special size solver named the weighted max size solver that can output the satisfying assignment with the least weights. And this size solver is very fast because it's equipped with different heuristic algorithms. And we set the values of all the leaf nodes as 1, so we get a fault graph like this. And the size solver can output the result because this result has the least weight. So this is exactly what we want. And because we want to find out the top K critical risk groups, so we can use a disconjunction operator to connect the current formula and the negation of the resulting assignment. And we get a new Boolean formula, and we put this new Boolean formula into the size solver, and we can get the top K critical risk groups. If we can get the failure probability of each component, and we can get a much better result because we can set the weight of Boolean expression as the failure probability. So far I have presented how we solve the former 2 problems in using our framework. Now let me show you how we automatically generate the improvement plans. So, for example, administrator may find some problem in her current deployment, and our framework offers the automatic repair engine. Administrators can write the specifications to express the goal on the improvement. For example, maybe she wants the new deployment has a failure probability lower than some number. And administrators can put this specification in our auditing engine, in our repair engine, and our repair engine can automatically generate the repair plans. So the key design behind our repair engine is the synthesis approach, and we can automatically generate the plans. So we did a lot of investigations to our framework, including case studies and comparison of fault graph analysis. Due to a limit of time, I only show you the result about comparison of fault graph analysis. We evaluated the fault graph analysis approaches based on different types of data center topologies. Let me show the result about the larger scale topology. So in this result, the y-axis is accuracy and the x-axis is runtime. And this point is one of the existing effort named the minimal cost set algorithm, which is very slow. And the bottom part included the results output by Indus system with different failure sampling runs. And this point is our result because we rely on the site solver, so we can quickly get the result with very high accuracy. So as shown in this evaluation result, our approach is 300 times faster than Indus system, and we can offer very accurate result. In conclusion, I first talk about the Indus system, and then I described how we propose the language framework, which is rep audit, and we can address the problems in Indus system. This is the end of my talk. Our system is open source. I'm very happy to answer any question. Thank you very much.
Interesting work. I wonder if you can encode the related failures. For example, the device A fails on the device B fails, or device A fails on the B fails in a certain way. Can you
So the question is whether we can dynamically capture, the failure ordering events.
No, sorry. No. So it's still statically, but there is some dependency between A and B.
Yep.
Can you encode the related failures that occur only together, or that need certain conditions to occur? For example, A fails only B does not.
Oh, I see your point. Yeah. So that's a very good question. So for our current design, we use a static fault graph, so which we cannot capture the information. For example, the ordering or whether some failure events have the correlation. But so this is a very good point, because we are trying to propose a system that can maybe leverage some for example dynamic fault graph to capture what you said. So to encode all the events that potentially have some correlation or some relationship using the dynamic fault graph. But in that case, I think the problem we meet is it's very challenging to collect such dependency information from your system log. So that's the challenge we meet. So that's the reason we haven't successfully built a very reasonable, dynamic fault graph to capture that information. But that's absolutely a next step, and we are trying to work on that direction.
But if you had this statistics rather than correlation, then how hard it is to
how to reason about that, right? Yeah. So So based on my understanding to this area, there have been several dynamic fault tree analysis approaches, but we may try to use the similar way. For example, use some very special site solver to speed up that, but we haven't considered that so far because we haven't built model so far. So the first thing is to do the encoding, and after that we analyze it to reason about to get the result we want. Right? Yeah, thanks. Yeah. Yeah. Yeah, no, so that's a great question. Yeah, so because we don't have so enough time to detail that. So okay, so you're asking this part, right?
Yeah, what are the basic objects that are being described?
So the abstraction is photograph. So photograph is the basic abstraction for this language, and we use the primitives to operate on this abstraction. So okay. So this part is the primitives we propose, and each primitive can operate the photograph. The object is the photograph instance, because each photograph is used to represent your target snapshot of interest during your service runtime.
So it looks to me like a graph was a collection of nodes with edges and leaves.
So maybe this example. So can you see the left corner of the program example? We use primitive to generate FT, which is an instance of photograph, because like what I mentioned, the photograph is abstraction, right? So we get FT, and in the last line of this program. Oh, sorry. So we run the primitive, and to get out the ranking list about the potential problem in this instance. So
I'll ask you more afterwards.
yeah, so I'm happy to talk with you about more about the details of this language. But,
Great, thanks again.
thank you.